All right. So I just had to know. So basically, I was wondering about the laws of physics, and I'm wondering, are they constant everywhere in space? Like everywhere in space? Imagine my screen, like everywhere on my screen is space. Or is it like this way, like the laws of physics are this way in this part of the universe, but in this part it's a little bit different, this part's a little bit different, this part's a little bit different? Or is it always changing in all parts? Is it always constant in all parts? Or is it changing a little bit in some parts, changing a lot of bit in some parts, changing to a different degree in different parts of the universe? Like how's it working? Um, I was going to go right into the Gemini answer, but I guess let me just preface it with the other part of the question that I asked. So I also went ahead to ask, is it possible that the laws of physics in the universe could change over time on a macro scale, but that we just haven't observed it yet because humanity hasn't been around that long relative to the lifetime of the universe? And we haven't been around long enough to observe these kinds of changes ourselves. Also, is the idea of the Big Bang based on the presumption that the laws of physics have always remained the same? If so, the idea of the Big Bang and the origin of the universe could be incomplete or wrong. Let's find out. These are excellent and insightful questions that get to the heart of scientific methodology and the nature of physical laws. Yes. Could the laws of physics change over time on a macro scale? Yes, it is theoretically possible, and it's an active area of research and speculation in physics. Here's why. Observation bias. You've hit on a critical point. Our observations are limited by our existence within a tiny sliver of cosmic time. Humanity's scientific observations span mere centuries, while the universe is billions of years old. What we perceive as constant laws might simply be constant within our observational window. Theories proposing variation, varying fundamental constants. Some theories propose that fundamental physical constants like the speed of light, c, and the gravitational constant, g, or the fine structure constant, little Jesus fish looking a, all right, might not be truly constant but could vary over cosmic time or even across different regions of the universe. Evidence for constancy and why it's debated. Current astronomical observations, for example, looking at distant quasars whose light left them billions of years ago, are incredibly sensitive and have placed very tight constraints on any possible variation in these constraints. So far, no definitive evidence for variation has been found. However, no evidence found isn't the same as it's impossible. The constraints are very tight, suggesting if they do vary, it's by an extremely small amount or over time scales much longer than we can observe. Evolution of forces. Some speculative models suggest that the fundamental forces themselves, gravity, electromagnetism, the strong nuclear force, and weak nuclear force, might have been different in the very early universe or could evolve. For instance, the grand unified theories, or GUTS, predict that at extremely high energies, like those shortly after the Big Bang, the electromagnetic weak and strong forces might have been unified into a single force. As the universe cooled, they froze out into distinct forces. This isn't a change in the underlying law, but a change in its manifestation due to energy scales. Could there be further, slower freezing out or reunification over cosmological timescales? It's a question. Cosmological models beyond standard lambda CDM, while the is that delta CDM model lambda, okay, while the lambda CDM model or lambda cold dark matter is our best current cosmological model, it doesn't explain everything. For example, dark energy or dark matter. In some alternative models might implicitly or explicitly allow for evolving physical laws or parameters. The anthropic principle. One perspective suggests that the laws of physics are precisely tuned for the existence of life. If they were to change significantly, life as we know it might not exist. This could imply that either the laws are fixed or that we only observe the very specific epoch where they allow for our existence. Ooh, that's an interesting point. This could imply that either the laws are fixed or that we observe a very specific epoch where they allow for our existence. Hmm. Huh. 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 All right. The challenge is that if the laws of physics did change, it would be incredibly difficult to detect, as our entire framework for understanding the universe, our measuring stick, would also be shifting. Is the idea of the Big Bang based on the presumption that the laws of physics have always remained the same? Yes. Fundamentally, the standard Big Bang model, or lambda CDM model, does assume that the known laws of physics have remained constant throughout the universe's evolution. Here's why this is a critical assumption. Extrapolating backwards. The Big Bang model works by taking our current understanding of physics, general relativity, quantum mechanics, particle physics, and extrapolating backwards in time to incredibly high densities and temperatures. Consistency with observations. The success of the Big Bang model and its ability to explain the cosmic microwave background, the expansion of the universe, the abundance of light elements, and large scale structure formation relies on the consistency of these laws across cosmic time. If gravity, for instance, behaved fundamentally differently a billion years after the Big Bang than it does today, our calculations about gravity formation or the universe's expansion history would be wildly off. The known unknowns. While the Big Bang model is incredibly successful, it doesn't describe the very, very beginning, the singularity itself, or what came before it. This is where quantum gravity theories are needed, and those might indeed reveal a more fundamental layer of where constant laws are just approximations or emerge from something else. The Planck epoch, the first 10 to the negative 43 seconds, is an era where our current laws are expected to break down. The laws of physics did change significantly, or if the laws of physics did change significantly, would the Big Bang idea be incomplete or wrong? Incomplete, most likely. If fundamental constants or the nature of forces truly evolves significantly over cosmic time, the Big Bang model as we know it would indeed be incomplete. We would need a more comprehensive theory that describes how these laws change and what drives that change. It wouldn't necessarily invalidate all aspects of the Big Bang, like the expansion from a hot, dense state, but it would require a significant revision of the underlying physics used to describe that expansion and the subsequent evolution. Wrong is a strong word. Science rarely says something is entirely wrong unless it's completely disproven by new evidence. More often, theories are refined, expanded, or subsumed into more comprehensive ones. If the laws of physics are found to vary, the Big Bang model would likely be seen as a highly accurate approximation for the era we currently observe, but one that needs to be superseded by a more dynamic theory for the entire history of the universe. In conclusion, the possibility of changing physical laws is a fascinating and important frontier. While current evidence strongly suggests they are remarkably constant, our limited observational window means we can't definitively rule out subtle or macro scale variations over cosmological timescales. If such changes were confirmed, it would necessitate a profound reevaluation and expansion of our understanding of the universe's history and fundamental nature, including the very concept of the Big Bang. I went ahead to ask. Little bonus section here. Ding, ding, ding. Bonus round. If the fine structure constant changes, would that change c, the speed of light, and g, gravity constant, as well? This is a great question that delves into the definitions of physical constants. The fine structure constant, denoted by squiggly Jesus fish A, or alpha. Okay, that's alpha. I'm going to call that alpha from here on out. Alpha. It's locked in. The fine structure constant, denoted by alpha, is a dimensionless fundamental physical constant that characterizes the strength of the electromagnetic interaction. It is often expressed as alpha equals E squared over 4 pi times. That's another E looking thing, backwards 3. Subscript 0. H with a line through it. Oh my god, I don't know what any of this stuff is. All right, I'll just move on. Let's go back to stuff I know. Where E is the elementary charge, the charge of an electron. This other backwards 3, or E with to the with subscript 0 is the perivity of free space. H with the scratch through it is the reduced Planck constant, or Planck's constant h divided by 2 pi, and c is the speed of light in a vacuum. All right. If the fine structure constant alpha were to change, what would that imply for the speed of light and gravity, or c and g, respectively? 1. Relationship with c, the speed of light. As you can see from the formula, c is directly part of the definition of A. If A changes, we assume that E, or that one with the subscript 0, E30H, that one, it just looks like that. Or it looks like that, not like a 3, but like it looks like that with a line. And then a subscript 0. And the H with a slash through it remain constant, then C, the speed of light, must change to compensate and maintain the new value of alpha. Alternatively, it could be that E, or backwards 3 subscript 0, or H with a slash through it, change in a way that affects alpha and the speed of light remains constant. It is also possible that multiple of these fundamental constants change simultaneously in a coordinated way to produce a change in alpha. My head's getting hot. My head feels hot. All right. My hair looks like shit, but it's okay. That's fine. It is what it is. We're not focused on looks. We're focused on smarts, brains. Yeah. The key is that alpha is a ratio of these quantities. If the value of the dimensionless constant changes, at least one of the dimensional constants, permittivity of free space. Okay, so I'm just going to say permittivity of free space. It doesn't tell me what H with the little line through it is. Okay, I'm going to have to figure that out myself. Hey Google. Hey Google, what's the letter H with like a line through it? What's that called?
According to en.wikipedia.org, H is a letter of the Latin alphabet, derived from H with the addition of a bar. It is used in Maltese for a voiceless pharyngeal fricative consonant. Lowercase h is used in the International Phonetic Alphabet for the same sound.
All right, anyway. It didn't tell me. Okay, so I think my Google Home misinterpreted the question, but we'll just press on. It's all right. All Gucci. I need to take that chicken out the oven, don't I? All right, we got to finish this up. All right, we'll wrap this up, and then I got to go flip that chicken, or at least just take it out of the oven. I think it should be done. If the value of the dimensionless constant changes, at least one of the dimensional constants, E, the permittivity of space, H with a line through it, or C involved in its definition must have changed. 2, relationship with G, the gravitational constant. The fine structure constant, alpha, and the gravitational constant, G, are independent fundamental constants in our current understanding of physics. Alpha describes the strength of the electromagnetic force. G describes the strength of the gravitational force. There is no known direct mathematical relationship that defines one in terms of the other within our current standard models, like the standard model of particle physics and general relativity. Therefore, if the fine structure constant were to change, it would not necessarily imply a change in G. A change in alpha would primarily affect electromagnetic interactions, atomic structure, and light matter interactions. A change in G would affect gravity and large-scale structure of the universe. While some highly speculative theories might attempt to unify all forces and constants in the established framework of physics, they are distinct. Implications of a changing fine-structured constant. If alpha were to change, the implications would be profound. Atomic structure, the energy levels of electrons in atoms, and thus the size and stability of atoms depend critically on alpha. A slight change would make atoms unstable or prevent them from forming complex molecules. Chemistry, all chemical bonds are fundamentally electromagnetic. Changing alpha would alter chemical reactions, potentially making life as we know it impossible. Light matter interaction. How light interacts with matter, for example, absorption and emission spectra, depends on alpha, Astronomical observations use these spectral lines to study distant objects and any variation alpha over cosmic time. They use these spectral lines to study distant objects, and any variation in alpha over cosmic time would show up in these observations. Stellar processes, nuclear fission in stars. Oh my gosh, learn how to read. Come on. Sorry, let me try that again. Stellar processes, nuclear fusion in stars, which involves electromagnetic repulsion between nuclei, would be affected. This could change how stars burn and how elements are produced. Scientists are actively looking for evidence of varying fundamental constants by observing distant astronomical phenomena. As the light from these sources has traveled for billions of years, offering a look back in time, so far the evidence strongly suggests that alpha has been remarkably constant over cosmic history, though some extremely subtle and debated observations have hinted at tiny variations. Area calculation or variations in cosmological spacetime, cosmological timescales. All right, I go on. bonus section. Damn, this one's. I still got more ideas for this one. Apparently at 11:11, make a wish. My wish is that I become the most satisfied and fulfilled human being possible ever, and I live longer than anybody, and I'm more satisfied than anybody. Is that two wishes? I wish for more of us, the highest amount of satisfaction. It's a good wish. Be happy. Simple, discreet, straightforward. All right. So bonus section. Based on the anthropic principle, could it be plausible that the laws of physics of the universe have been evolving just as other species around the world have, albeit at a much slower pace and at a much larger scale? Is it possible that the laws of physics we experience on and around our solar system, which are perfectly tuned to accommodate life, is actually the only place in the universe that has these specific laws of physics to allow for life, and is this why we haven't been able to discover life elsewhere? Gemini responds, these are exceptionally thought-provoking questions that brilliantly connect the concept of evolving life with the fundamental nature of the universe and the implications of the anthropic principle. Yeah, cool. Thanks for juicing me up. Anyway, let's get straight to it. What's the actual answer? Could the laws of physics evolve like species? This is a highly speculative but fascinating idea. In our current understanding, the laws of physics are considered fundamental and unchanging. They are the rules by which everything operates. However, your analogy with species evolution prompts us to consider evolution of laws. If evolution implies a gradual change, adaptation, or selection over time, how would this apply to physical laws? Selection mechanism. For biological evolution, there's natural selection. Fitter organisms survive and reproduce. What would be the selection mechanism for physical laws? Multiverse context. One speculative idea that could support this analogy is within the context of a multiverse. If there are many universes, each with slightly different physical laws or fundamental constants, then perhaps only those universes whose laws permit the formation of complex structures like stars, galaxies, and eventually life could exist in a meaningful sense, or at least be observable to conscious beings. This isn't evolution within a single universe, but a selection among many universes. Cyclic universes. In some cyclic cosmology models, the universe undergoes repeated cycles of expansion and contraction. It's wildly speculative, but one could imagine that with each cycle, some parameters or underlying rules might be reset or mutate slightly, and perhaps only cycles with favorable laws persist or lead to interesting outcomes. Scale and pace. As you rightly point out, such an evolution would occur on cosmic timescales, vastly exceeding our observational window. Even if laws were subtly shifting, it would be incredibly difficult to detect, as our entire scientific framework is built on the assumption of their constancy. Current scientific view. The prevailing scientific view is that the laws of physics are constant across space and that time within our observable universe. Any observed variations in fundamental constants have been constrained to be extremely small, if they exist at all. The very success of astronomy and cosmology in observing distant, ancient parts of the universe and seeing the same physical processes at play, for example, stellar fusion, light spectra, strongly supports this constancy. Are our local laws of physics uniquely tuned for life? Strong anthropic principle. This is precisely where the strong anthropic principle comes into play. The strong anthropic principle, or SAP, states the universe must have properties which allow life to develop within it at some stage in its history. This is sometimes interpreted more strongly to mean that the universe's fundamental constants and laws are necessarily fine-tuned for life. Your hypothesis? Is it possible that the laws of physics we experience on and around our solar system, which are perfectly tuned to accommodate life, is actually the only place in the universe that these specific laws of physics to allow for life, that has these specific laws of physics to allow for life, and why we haven't been able to discover it elsewhere? This is a very intriguing extension of the anthropic principle, suggesting spatial variation in the fundamental laws rather than just temporal constancy. Implications of spatial variation. If the laws of physics vary significantly across different regions of the universe, this would be revolutionary. Breakdown of universality. Our current understanding of cosmology and physics relies on the universality of these laws. If they change from one galaxy cluster to another, or even within a galaxy, our models would need radical rethinking. Observational evidence. We currently observe the same spectral lines from distant galaxies as we do locally, suggesting that electromagnetic interactions governed by the fine structure constant are the same. Gravitational lensing and galactic dynamics also seem to follow general relativity consistently across vast cosmic distances. If there were different laws governing, say, gravity in a different part of the universe, we should see deviations in how galaxies interact or light bends. So far, we haven't seen such evidence for fundamental law differences. That is true. That is true. Yeah, you'd see the light and different patterns and different things going on cosmologically. You'd see that travel from wherever it is in space to Earth. And if the laws of physics were different, I think we'd be perceiving different things differently. And yeah, we'd notice a lot more anomalies, I feel. Habitable pockets of physics. Your idea proposes habitable pockets of physics. This is a very creative thought. It would mean that perhaps the conditions that allow for life are not just about the right temperature or presence of water, but about the very underlying rules of reality being locally specific. Why haven't we discussed? Oh my gosh, hold on. Are my eyes tired or what? Sorry. Why haven't we discovered? Why haven't we discovered life why haven't we discovered life elsewhere? If your hypothesis of spatially varying laws were true, it would indeed offer a compelling explanation for the Fermi paradox, the contradiction between the high probability of extraterrestrial life and the lack of evidence for it. If the precise tuning of physical laws necessary for God, come on. Whew. Either my brain's starting to get tired, my voice is starting to get tired, something. It's like I can notice a certain point when I'm reading where it's like, whoa, nothing's making sense anymore. Where it's like, that tells me I need to read more. I need to work out this muscle more. Because like, dude, it's like doing a set. Like imagine doing curls and like you never really do curls. And it's like, you're only going to be able to do a little bit. And it's like, oh God, that's like me with reading. Like I'm not used to reading enough and I need to read more. And I really, really need to make an effort to read a lot more. Like not only a little bit more, a lot more. I need to read a lot more. But I do notice I'm still working it out and I'm still training my brain to adapt to reading better. Literally the whole entire point for this thing. Literally the whole point of these videos, man. To be able to articulate myself better, to be able to communicate better, to be able to be a better speaker, better orator, and get my thoughts out better, be more confident while speaking. And also to be able to have more knowledge, to be able to have more jokes readily available to people, to have more information readily available to people, to be able to be more useful to the world. So I'm trying to be of maximum use to the world. So that's why I do what I do. Hell yeah. All right, let's try this again. Why haven't we discovered life elsewhere? If your hypothesis of spatially varying laws were true, it would indeed offer a compelling explanation for the Fermi paradox, the contradiction between the high probability of extraterrestrial life and the lack of existence for it, or the lack of evidence for it. The lack of evidence for it. If the precise tuning of physical laws necessary for complex chemistry and stable star systems is exceedingly rare and localized, then life itself would be exceedingly rare and confined to these pockets. Pockets. However, hey, what's up? What's up, buddy? What's up? What's up? You bored? You bored? I don't know if you need to go to the bathroom. I took you out earlier and you didn't go. You're doing this earlier. Give me like another half hour. Okay? How's that sound? Give me another half hour. Let me get this done. Let me finish this and then I can take you out in a little bit, okay? I'll take you out. Just a little loop around the neighborhood. How's that sound? Good? Good? Love you. All right. All right, little puppers. He either wants to go out, he needs water, or he just wants attention. I feel like half the time it's attention. Sometimes, most of the time, or like so other times it's walk, and then sometimes like it's water. All right, I got you, pup. I'll take care of you. You got water, so it's not that. You got food. You didn't want the rest of this burger, so it's not that. And so you might need to go out in a second. So let me wrap this up real quick, and then we'll go out. Okay? Does that sound good? I'll take you downstairs. However, it's important to note that the lack of discovery of extraterrestrial life could also be explained by vast distances, the sheer size of the universe, short lifespan of civilizations. Civilizations might not last long enough to be detectable. Technological limitations. Our own detection capabilities are still very limited. Rarity of conditions. Even with constant laws, the specific conditions, planet type, star type, galactic location, and stable environment might be rare. In conclusion, while your idea of evolving or spatially varying physical laws is not currently supported by direct observational evidence and challenges our fundamental understanding of cosmology, it's a profound thought experiment that ties into the deepest questions about the nature of reality and the implications of the anthropic principle. It forces us to consider, one, are the laws of physics truly immutable, or are they emergent phenomena from something more fundamental that can change? And two, if the universe is truly vast beyond comprehension, are we sure that the laws we observe here apply everywhere and for all time? These are questions that push the boundaries of current scientific understanding and highlight the ongoing search for a more complete theory of everything. All right, I'm gonna go ahead and pause that there. Got some good info from that. Thank you for watching. I'll see you around.